Hello, this is Bernie Zeigler, and this is part two of the talk on why we should develop simulation models in pairs based on the presentation I gave at the 50th anniversary Titan SOC for the Winter Simulation Conference in December 2017. Well, so far in part one, we've discussed the motivation for building both models, target and simpler model, when it's hard enough to build one. And the reasons given had to do with the fact that the simpler model can add value in many ways, such as shown here. But there are conditions required to achieve any valid simplification. And generally, these pertain widely in their uniform structure within the blocks that we are aggregating, and in difference of the components within the blocks to interactions with other block members in other blocks as well. We gave an example applied to brain simulation where we made the analogy to the aeronautical use of miniature wind tunnels to scale up to the actual full-scale design of airplanes. So now let's go on to our second example, a combat modeling of attrition using multi-resolution, where we consider encounters between high-level combat units with the win-loss probabilities and durations of the fighting and the remaining force after end of the battle determined from lower-level unit models. For example, we have a red force encountering a blue force, and we'll imagine that each one is composed of tanks, and we'll examine the interaction among the tanks. So here we have a base model with single weapon units, the tanks, and one lumping where we consider each force as a brigade, and the lump model consists of brigade units. And this model can be considered as a component model for the base model, but also itself can be broken down into models of single unit elements, and that would be a second breakdown or second lumping. And we could also compose these lumpings to consider the base model broken down into unblocked but a larger array of single unit elements. So we'd like to examine the uniformity and indifference conditions in this case of combat modeling. And we have two opposing groups and a base model in which individual tanks are arrayed in these groups. And we're constructing a lump model in which these tanks are grouped into components at the lump level, and therefore we have two lumped components, the red and the blue. And at the base model level, the interaction among the groups is mediated by shots fired by the tanks at each other. And at the lower level, we have also shots fired, but there are no tanks, so we're generating these shots in a lump manner that reflects the way they're produced in the base model. In order to do that, we need to have the uniformity and difference conditions satisfied, and here they take the form of two forms: emitted fire uniformity. Every unit distributes the same total fire volley to the opposing group, and received fire uniformity. Every unit receives the same fire volley from the other group. In other words, for example, a tank receives the same amount of firing from the other side without knowing, without knowledge of what the individual members in firing at it. And that's true for every tank or unit in the block. This is the way the fire condition, the uniformity and indifference conditions looks in this case. This allows us to construct a homomorphism which is a mapping from the states of the base model to those of the lump model. And you can see here that in the base model we're keeping track of individual tanks, and transition has to do with the striking of one tank or killing of one tank from the opposing side. And the mapping has to do with aggregating, so we get the number of tanks on each side, and a preservation of the transition in the lump model would be that exactly one tank is destroyed in the same way that one particular tank is destroyed in the base model. This approach to a formal approach to the mapping and the requirement for transition and the underlying uniformity conditions allows us to avoid what we call ontological mismatches. Quoting from a recent paper, current high-resolution simulations such as Janus that employ a time-step approach for simulating target acquisition do not explicitly keep track of the times at which line of sight is established or lost for specific target observer unit pairs, which is needed for the typical Lanchester-type aggregated replay model. In other words, the kind of lump models that we're talking about, using reliable statistical estimation techniques for determining model parameters. So the critical idea is that in these high-level resolution simulations, line of sight is established in a step-by-step manner, and there's no explicit record of line of sight. And if we have to estimate what that is, we are in a situation where we're not as able to produce a valid morphism as if we actually have that kind of line of sight characterized. Well, in this case, it's quite easy to see how the conditions required for valid simplification might be violated. For example, the uniformity condition could be violated if tanks in the same block have different vulnerabilities, different shielding from power, and if their firing power differs, so some are high-powered and some are low-powered, so that they're not all of the same structure. And for indifference, we can see a certain easy kind of case in which front-line tanks receive different amounts of fire than rear-line tanks, and so that the emitted and received fire uniformity might easily be violated. So the question we want to deal with is how can we work with situations in which the strict requirements for lumpability are only approximately satisfied. So to phrase the problem, we imagine we are dealing with the base and lump model in a particular experimental frame, which represents the conditions under which we're simulating these models, and the question we're asking of the base model, and we want the lump model to give that same answer. But we have a departure from lumpability, which we can measure, and the assumption is that we can measure it, and the effort must be to develop metrics to be able to measure such departures. And given such a departure, what is the error that can be expected from the lump model in terms of the same behavior in answering the question of the base model? We can imagine a spatial mapping in which we have a horizontal axis, which is the departure from lumpability, using the metric that we have, where zero value would mean that the structural and indifference requirements are exactly satisfied. And at that point, we would have zero error, but for bigger departures, we would expect that the error increases. And in fact, we find that the error tends to increase linearly with departure from lumpability, and with oscillations and fluctuations that arise from any stochastic considerations in the model. But they achieve some kind of background error level after a certain sufficient departure, where the background level is the error that can be expected when the models are totally unrelated to each other. So we do have an expanded region called the lumpability zone, in which we can expect that we can get not necessarily zero error, but small error, depending on the departure from lumpability. And this can greatly increase the likelihood that we can create lump models for base models that don't exactly satisfy requirements, but do satisfy them to a reasonable extent. And reasonability is what is expressed in the extent of the lumpability zone, how much departure from lumpability can be tolerated while still producing some error that is usable for that, in that case, for answering the question that is being addressed. In our final example, we're looking at a multiprocessor architecture in which processors are interconnected by a communication network. And our question is the effect of the properties of the interconnect on speed up. Here we have n processors, each of which goes through a cycle in which it does computation and then waits for requests data and waits for data. And they're all assumed to be having the same properties, such as having the same computing time and the same properties in relation to the communication network. So the speed up is measured by the sequential time to do a job over the parallel time. And assuming the job takes a certain computation time, then the sequential time is n, where n is the number of processors times that communication time. But assuming that the job can be done in parallel, it only requires a computation time. However, there may be required communication, and that incurs a delay. So the amount of delay reduces the speed up. And we have the speed up relative to the maximum then is relative speed up, which is the speed up divided by n. And we see that that can be 1 when the computation time is much bigger than the communication delay, but it veers away from 1, gets smaller as the communication delay increases. And since it's a function of the number of processors and the properties of the communication network, we need to do simulation to actually get that dependence. Or we can develop a lump model and predict what that dependence is. In this case, we block all the processors lump all the processors into one block, and consider that block then modeled by a Markov process, and the block receives a certain input rate of data and processes and produces requests at a certain rate which go to the communication network, and that in turn receives those messages and has a queue that stores the messages until they can be processed, and that then results in an output rate of messages back to the block of processors. So we have the n processors blocked into one block and the communication network considered as another block, and those two interact. And we need the conditions for uniformity and indifference to hold to develop a lump model. In this case, we can analyze the model, and basically there are two regimes which come out of this consideration. One in which the processing is undergoing a normal manner, and that is when the processors are all close to 100% active all the time, in which case the speed up is about n. And the other case in which the processing is congested and only one processor is active at any time, and in that case the speed up goes down to 1, in which there is effectively no speed up. It's interesting that the speed up in the normal case is lowered by the variance in the processing times, and we'll come to see how that is can be considered a result of the departure from uniformity in the processing times. Now, this example allows us to understand how the departure from strict lumpability requirements affects the ability of the lump model to predict the effective speed up, the relative speed up of the base model. Now, for uniformity of structure, all the processors have the same property. Here, let's assume the same processing time. And then, in terms of indifference, we have the block of processors and the COMNet, the place at which indifference can arise is the response of the COMNet to the requests of the processors. And indifference would require that that all such responses are treated, such requests are treated equally. That is that there's no priority for processors in the underlying queuing discipline. Now, requirement 1 is violated when the processors don't have the same processing time, in which case they have varying processing times, and we can show that the departure there is measured by variance, and we can show that it reduces the speed up. And requirement 2 is violated when the processors have prioritized access to the network, so that the network is cognizant of the identities of the processors and treats them differently, and that violates the requirement for indifference. So it turns out that there's a special trick here that still allows the lump model to predict correctly what the effect on the speed up is. And in this case, it's we can look at the processing by the processors as in an iterative fashion, in which the first processor, the highest priority processor, is treated and analyzed as if it were acting alone, and then the next processor in priority is given a smaller bandwidth. That amount of processing or queuing that remains after the first processor is finished, and so on down the line, so that there's a neat way of predicting the actual effect of prioritization. However, the general case in which the processors are treated differently other than priority is much more complex and requires iteration to a fixed point solution. Well, we said that the pairs of models approach really is a step toward considering problems in terms of multi-resolution model families. For example, here is a global warming family where we're organizing the models by the questions that they answer, and the model components also are related through morphisms and approximate parameter morphisms. A parameter morphism is a morphism that also relates the parameters of the base model to those of the lump model. And that often is how we develop simplified models. We derive their parameters from the parameters of the base model that we're simplifying. So here's a little illustration where we have a number of different questions that are related to global warming, and each question is answered by a certain model family. But the model families can intersect, and the same components can be used in more than one family. So the components are organized by inclusion relations. For example, a storm intensity increasing model to answer questions about how global warming contributes to increasing intensity of storms. This family consists of models such as the greenhouse effect and the storm model that are also used by other models, other families. So it should be pretty clear that to deal with multi-resolution families, we'll need a set of tools that go beyond the usual simulation tools that we're familiar with. And in particular, let's examine how we can check morphisms. In particular, we'll look at a homomorphism with computational means. And here we have a pair of models, a base model and a lump model. And remember, the idea is that if we start in a base model state and make a transition, it goes to another state. And if we map the first state to the lump model state and allow it to take the same transition, then the lump model state it goes to should also be corresponding to the base model state under the corresponding mapping, the putative homomorphism. And if this is true, then this parallel tracking of the base model state by the lump model will continue without error. However, if there is an error, that at some point this correspondence will not hold, and there may be an error introduced, and that error could grow, or it could reach some kind of steady state level, which might be tolerable. So how do we check this kind of situation? Well, basically, we now need to run the base model and the lump model, simulate them and run them in parallel, one to the other, and make corresponding checks at the right moments to see if the mapping is being preserved as required. So here's a listing of the sequences in which we simulate the two models, and essentially we're doing an alternation between one and the other, and if in parallel, then we could do it without making that kind of alternation. And here we have a little illustration that we will be testing the base model in a certain transition, testing the lump model in the corresponding state for the same kind of corresponding transition, and checking whether the correspondence holds, and deciding if it deviates and the homomorphism is not satisfied, and if it continues to hold over all the states we check, then we have more confidence that it will hold in general. Well, this computational approach to morphism checking leads to a more general concept of workflow for approximate morphism evaluation. Here it is outlined where we start with parameters that inform the construction of a base model itself, producing parameters that go into help construct the lump model that is supposed to correspond to it, using the parameter morphism and the values from the base model and outside the starting process. And with the two models available, we can start up the simulators with default states that allow them to get started. And once established, we can inject initial states that are meaningful for a particular run, and run the simulators and get results, and continue until enough runs have been accumulated. This leads to the concept of operations and workflow orchestrators, where we need more than one model is to operate on, leading to n-ary operations. For example, making the simulation with simulator, base model, lump model, and the experimental frame would require starting the simulation, running the simulation for a number of iterations and getting results. For evaluation, we might require the base and lump model be compared within the same experimental frame, and we might compute the lumpability zone based on the base and lump models and the experimental frame, and might compute the background level for the base model within the experimental frame, so that we have a basis to compare the errors that are computed in the lumpability zone computation. And for workflow, we have, for example, implications at starting the simulation for base lumped models. We'll start the simulation of the base model and start the simulation of the lump model. When we compare the base model with the lump model, it has to start the simulation for the base model and lump model, which in turn must start each one off. So a number of implications that can go into constructing a workflow and an orchestration of various processes that have to be undertaken to do this approximate morphism evaluation. Finally, let's consider some takeaways from the discussion of pairs of models approach. The question we addressed was, why put in twice the time and effort to develop two models rather than one as in the conventional approach? Well, working with the base model, lump model pairs right from the start may be better than constructing a target model and later developing a simpler one where it has to be done under stress. And of course, there's value in doing the lump model from the beginning. They give more easily obtained insight, be more general, be used to test the target model, proxy for that target, explain that target's behavior, and in general, because it's simpler, offer a wider variety of possibilities to work with in modeling the real system. Benefits of a multi-resolution family of models is a generalization of working with base and lump models in pairs. They can be organized by approximate morphisms. Such organization allows you to perform mutual cross-calibration of models where you get information about one and cross-calibrate to provide information about another, both directions, base to lump, lump to base. Paul Davis has been a proponent of this approach in the defense modeling and simulation community. Avoid harmonization issues in underlying ontologies. We've talked about an illustration where models may be developed with different assumptions, and then it is very hard to correlate and to actually put them into some correspondence as we'd like to with the morphism. And it's easier, therefore, to reconcile and correlate model behaviors. But we need some principles of valid simplification to support this concept of morphism and approximate morphism. Conditions required, we talked about uniformity and coupling, indifference, and approximate morphisms allow us to relax the conditions and open up, therefore, a much wider set of possible pairings, because the conditions for uniformity and coupling and indifference are pretty strict. That leads to constructive agenda, where we need to develop software tools to implement the theory, to make it possible to work with Bayes and lump models and with multi-resolution families of models in a more easy and productive manner. And the tools have to be developed in the future. So this talk is one to allow and encourage further development in this area. Thank you very much for your attention. For more in-depth, there are videos that go into discussion of exact and approximate morphisms, and the more detailed discussion of simulation morphisms and model property preservation. Some books are coming out. The third edition of Theory of Modeling and Simulation will have much more to say on this topic from a theory point of view, and then a book coming up on model engineering will have a chapter on simulation-based evaluation of morphisms for model library organization, and these books are coming out in the year 2018. Thank you.